So for topic 8, we're going to look at how to graph the cotangent and tangent functions. And we're going to start off with trying to justify why the graph of the tangent of theta looks the way that it does. So the key with understanding the graph of the tangent function is to keep in mind how it's been defined. If I can get my pen to show up here. And what we want to remember in particular is that the tangent of an angle theta has been defined in the xy plane as the ratio of y to x, or y over x. And so the key to understanding the tangent function then is to look at the unit circle. And the first important thing to look at is the quadrantal angles. So 0 degrees or 360 degrees, 90 degrees, 180 degrees. That's a horrible unit circle, isn't it? And 270. So the y and the x coordinates at 0 degrees or 360 is x is 1, y is 0. Up here at the 90 degree mark, as we rotate through 90 degrees, we know x is 0, y is 1. At 180 degrees, we know that x is negative 1 and y is 0. And at the 270 degree mark, or 3 pi over 2 radians, we know that x is 0 and y is negative 1. So the first big thing to think about if you're thinking about what the graph of the tangent function needs to look like is the denominator here. So this is where things can go wrong. We have an x in the denominator, which means that every time x is 0, the tangent function will be undefined. And so we can see that x is going to be 0 at the 90 degree mark when we rotate through the 90 degrees. It'll also be 0 if we rotate backwards to negative 90 degrees. So at the 90 degree mark, or pi over 2 radians, I don't know if in the video you can see it, but the x-axis here is ticked off in terms of radians. So I have pi over 2 radians, or 90 degrees. And here's negative pi over 2 radians, or negative 90 degrees. X will be 0, the tangent function will be undefined. And that's going to happen at 90 degrees. If we rotate another 180 degrees, we'll be at 270 degrees, or 3 pi over 2 radians. We'll get another spot where the tangent function's undefined. And we rotate back around. This will continue to happen over and over again. If we are here at negative 90 degrees, so we rotate to negative 90, we rotate another negative 180 degrees to negative 270 degrees, or negative 3 pi over 2 radians. We'll have another place where the tangent function is undefined because the x-coordinate will be 0 and division by 0 is undefined. And the key is, if we remember from graphing in pre-calculus, that when we get division by 0, if this isn't some sort of removable discontinuity, we wind up getting vertical asymptotes in those spots. So that's not going to change because we're working with a tangent function. We have an x in the denominator causing a division by 0. This is going to generate vertical asymptotes for our function. So I'm going to draw just a few of those in. And what we want to understand is, because we can rotate as many times as we like, these vertical asymptotes, as we rotate around the unit circle, will just repeat over and over again infinitely far in both the positive theta direction and the negative theta direction. On the theta axis, this is the theta axis. So with the tangent function, the inputs are angles, so we have the theta axis, and the outputs are side ratios on right triangles. So one more vertical asymptote. It's not very efficient to draw them in, but I'm doing it anyways. So that's the first big thing to recognize, and we want to recognize that those divisions by 0, everywhere where the x-coordinate is a 0, so that we get division by 0 for the tangent function. We want to recognize that those are separated by 180 degree rotations. So if I'm at one division by 0, if I rotate 180 degrees, I get to division by 0 again. So the distance between these vertical asymptotes is always going to be 180 degrees or pi radians. 180 degrees or pi radians. 180 degrees. And these would continue over and over again infinitely far in every direction. So vertical asymptotes, that's the first key feature you'd want to pencil in on a tangent function. So the next thing to look at that is important to look at is when is y equal to 0, because when y is equal to 0, we get 0 over either a 1 or negative 1, we get 0. So when is y equal to 0? Well, that happens here at 0 degrees or 360 degrees. In fact, at 0 degrees, x is 0. Any angle coterminal with 0 degrees will have y equal to 0. And any angle coterminal with 180 degrees will have y equal to 0. So that happens at the 0 degree mark. We get y equal to 0. So the ratio y over x will be 0. And then if we rotate through 180 degrees, I guess I should clean this up a little bit, give myself a quick clean unit circle. So the y's are going to be equal to 0 on the unit circle here. Messed that up here. And right here at -1, 0. And these are going to be every 0 degrees, 180 degrees, 0 degrees, -180 degrees. And they're going to repeat themselves over and over again. So here's the -180 degree mark right here, or halfway between the vertical asymptotes. Halfway between the vertical asymptotes will be where the y coordinate is equal to 0. It'll always be a 90 degree rotation away from your vertical asymptotes. So the tangent function is going to have to pass through these points. So the next thing to think about, in my opinion, in terms of graphing the tangent function, is to look at the unit circle and think about what does the sign of the tangent function need to be. So graph a unit circle again. And we know that the tangent function is going to be that ratio of y to x. So in quadrant 1, we know that x is positive and y is positive. So the ratio y divided by x is going to be positive in quadrant 1. But in quadrant 2, x is negative and y is positive. So the ratio y over x will be negative. In quadrant 3, both x and y are negative numbers. So the ratio y over x will be positive. And in quadrant 4, we will get x positive, y negative. So the ratio y over x will be a negative ratio. So what we can see is every 90 degrees, the sign of the tangent function has to switch between positive and negative. So between 0 and 90 degrees, this is the 0 degree position. This tangent function is positive, but between 0 and -90 degrees, the tangent function is negative. And the sign of the function is going to oscillate between positive and negative as we move along the theta axis. So that's the next key feature to think about. Now, from pre-calc, you expect a function to kiss up along its asymptotes. So if the tangent function, just from what I know in pre-calculus right now, I would expect, because the tangent function is positive between 0 and 90 degrees, I would expect my tangent function to come through this 0 point and sweep up along its asymptote. And because it's negative here, I would expect it to sweep down along its asymptote. Positive, negative. So now, just based on what I know about asymptotes, I'm expecting the tangent function to do something like this. but I think we can justify that it's going to have that type of behavior. So what we can do is, again, think about on the unit circle what's going on as we approach a vertical asymptote. So let's say I'm approaching 90 degrees. And let's look at the limit as the input angle goes to 90 degrees of the ratio y divided by x. This is the tangent ratio. Tangent of theta is y over x. Well, as you approach 90 degrees, we're approaching on the unit circle the ordered pair 0, 1. So as we approach 90 degrees, we expect the y value to become 1, and it would be 1 over the limit as theta is approaching 90 degrees. Where does the x-coordinate go? The limit as theta goes to 90 of the x-coordinate. Well, the x-coordinate is getting closer and closer to 0. So if the x-coordinate gets closer and closer to 0, let's say 0.1, 1 over 0.01, what are we going to get from this? 1 divided by 0.1 is 10, 1 divided by 0.01 is 100, 1 divided by 0.000001 equals 1, 1, 2, 3, 4, 5 equals 100,000. What we see is as x goes to 90 degrees, as theta goes to 90 degrees, the x-coordinate gets closer to 0, but the ratio 1 over x is getting infinitely large. So we're sweeping up along this vertical asymptote, and as we go to 90 degrees, as we approach this vertical asymptote, the only thing that changes is the y-coordinate is negative. So these ratios would have a negative sign in the numerator, which would make these outputs negative outputs instead of positive. And in fact, the tangent function has odd symmetry. It has symmetry with respect to the origin. So the only other really important thing to look at on the tangent function, in fact, let's clean this up and look at it. So I'm going to wipe this mess free. We'll pop in the tangent function graphed by GeoGebra so it's nice and clean. Here's the tangent function with a few of its vertical asymptotes. So here's some vertical asymptotes no longer drawn by hand by me. So there is another key feature when you're graphing the tangent function that's really important to look at. We want to establish that we've got these vertical asymptotes, that halfway between vertical asymptotes we have outputs, side ratio outputs of 0 occurring. There's one other important spot to look at, and it's going to be the places on the unit circle where the x and y either are the same or vary by a sign. So 45 degrees is important. And at 45 degrees, or pi over 4 radians, and that would be halfway. This is 0 degrees. This is 90 degrees at this vertical asymptote. So 45 degrees, or pi over 4 radians, is exactly halfway between. We know at this point the x-coordinate is root 2 over 2 and the y-coordinate is root 2 over 2. So that tells us that the tangent of 45 degrees, which is the y divided by x, is going to equal 1 because the x and the y-coordinate are the same. So at 45 degrees, halfway between the 0 and the vertical asymptote, I get an output of 1 on the tangent function. So I input 45 degrees, the output's 1, or I input pi over 4 radians, the output's 1. When we're graphing transformed functions, transformed tangent functions, this will be a key point to keep track of. This will be a key point to keep track of. The vertical asymptotes will be key points to keep track of. And the other key point to keep track of when we're graphing is negative 45 degrees. And here, where you are just reflecting 45 degrees over the x-axis, the x-coordinate is still going to be root 2 over 2, but the y-coordinate is negative root 2 over 2. And the result of that is that the tangent of negative 45 degrees is going to equal negative 1 instead of positive 1. So here at negative 45 degrees, halfway between the 0 and the other vertical asymptote, exactly halfway between. This is negative 90 degrees and 0 degrees. We're going to get an output of negative 1 instead of positive 1. And these are key features to keep track of on the graph. So the only other thing really that we want to talk about before we end this, let me wipe this clean, is the domain, the range, and the period. So the domain of the tangent function. And it's easier probably to describe the domain in terms of what theta can't be than what it can be. So we're going to do that. We're going to say theta cannot be. Everywhere where we get a vertical asymptote, that was a value of theta that we couldn't use. And those happened at 90 degrees. And negative 90 degrees were the first two, but what we want to remember is that they were exactly 180 degrees apart. These are always 180 degrees apart. These vertical asymptotes are always 180 degrees apart, and the inputs associated with each vertical asymptote, the x equals equations, those are what we can't use. So it's really going to be, we can't use 90 degrees plus 180 degrees times k, where k is any integer. You add any integer multiple of 180 to 90 degrees, you're going to wind up at one of the other vertical asymptotes. They're all separated by 180 degrees. So that's what theta can't be. The range, however, is our side ratios, and the function itself, f of theta, when we look at it, we see it goes to negative infinity and goes to positive infinity with no restrictions. So the range, that was a horrible infinity sign. You'd think after 20, 30 years of drawing them, I could draw them, but I can't. So domain and range are relatively simple, and the period of the tangent function is going to differ from the period of the sine and cosine, because we see is every 180 degrees between the two vertical asymptotes, the picture of the tangent function completely repeats itself. So we get a period of 180 degrees, or pi radians. And up here for domain, we also could have described it in terms of radians. We could have said theta cannot be 90 degrees is the same as pi over 2 radians plus any integer multiple of 180 degrees, but pi radians is equivalent to 180 degrees, and we would still say k must be an integer.